Hello, everybody. Welcome. Today we're looking at quest number 7, problem 10. So quest 7, problem 10, as it says at the top. And we've got this situation. We have these two blocks that are connected to each other. There's a cable in between them, which doesn't stretch or anything, and there's an applied force up the ramp. We know the masses, we know the angle of the ramp, we know the acceleration of the system, all from that picture. So we're asked to find the force pulling up on the blocks, that applied force F. So there's two ways you could do this. There's two different ways you can do this. We've been talking a lot about systems of objects recently, a lot about systems. So this is a two-object system here. There are two different objects that are connected and their motion is dependent on each other. So you can either look at it from an individual object lens, where you draw free body diagrams for every single object, both of them in this case, or you can zoom out a little bit and you can say, you know what, I'm just going to call that whole thing my object and look at it from there to simplify my problem. And that's what I'm going to do today. Okay, you could go through and do it individually looking at each object and you should get the same answer. But I'm going to simplify things and I'm going to do it using a system. So let's take this whole thing, both these blocks and the cable in between them, as my system. Okay, that system has a total mass, which I'm writing as capital M, which equals M1 plus M2, right? That total system has a mass that is equal to the sum of both those masses. Okay, so now let's draw a free body diagram for this new system that's bigger. Okay, we have our object, which is on an incline. We have our weight force, which points down. Our force of gravity, which is equal to capital M times G. We have our normal force, which points perpendicular to the plane, the inclined plane. And we have our applied force, which points parallel to the plane. That's what we're trying to solve. That's why I put it in red. Just a reminder that up and down the ramp is the parallel direction, that is parallel to the plane. And into and out of the ramp, like this, is the perpendicular direction. Just a reminder that that is parallel and perpendicular. So we've drawn our free body diagram. Now we look at this and say, this FG, this gravitational force, is not along one of our coordinate systems. It's not along one of our coordinate system lines. It's not parallel or perpendicular to the ramp. So let's resolve it into its components. So let me break out green. This is going to be right here. This is going to be capital M times G times the cosine of the angle. And we have this one that points down the ramp. That is going to be capital M times G times the sine of the angle. Okay, so now everything is parallel or perpendicular to the ramp. So we can begin to solve. One thing we know is that the acceleration points up the ramp. So I'm going to call that our positive direction, just a thing to keep in mind. So we have our free body diagram. Everything is all situated. Now we can start to do Newton's second law. I'm going to do this in purple. So now we can start to apply Newton's second law. You know, the sum of the forces parallel to the ramp must be equal to the total mass of the system, which is capital M, times the acceleration. Okay. Now comes the question of what is our net force? What is the sum of all of our forces? So since we're calling up the ramp the positive direction, that means that F minus capital M, the total mass, times G times the sine of theta must equal the capital M, which is the total mass of the system, times the acceleration. Okay, all of our forces up the ramp minus all of our forces down the ramp must equal MA. So let's start to rearrange some stuff. That means that this applied force must equal the total mass of the system times the acceleration of the system, plus the total mass of the system times the acceleration due to gravity times the sine of the angle of the inclined plane. We can do a little rearranging here. if we factor out this total mass, that means that F equals the total mass. Ooh, that was ugly. Total mass times the acceleration of the system plus acceleration due to gravity times the sine of theta. And we are almost there. Now we can go up here and we can say F, actually I'm not gonna have room to write all this. Let me keep going down. That means that F must be equal to, this is gonna be M1 plus M2. It doesn't really matter right now which one you call which. Later it will matter, but right now it doesn't matter. Times the acceleration of the system plus the acceleration due to gravity times the sine of theta. Now we can plug some numbers in. Now we know all those quantities, so we can plug numbers in. I'll switch to black. F is equal to 26. I'm going to call this M1 and this M2. Like I said, for right now, it doesn't matter. For the next problem, it will for number 11, but we're going to call that like that for now. So that's 26 kilograms plus 45 kilograms times the acceleration, which is 3.1 meters per second squared, plus the acceleration due to gravity, which is 9.8 meters per second squared, times the sine of our angle, which happens to be 32 degrees. So we can plug this into our calculator. And remember, when you're plugging things into a calculator like this, that you are super careful about parentheses, because this doesn't think. You have to tell it exactly what you need it to do. So we get 26 plus 45 times 31 plus 9.8 times the sine of 32. I get that the applied force is 588. Oh, that was a bad 8. 588.8 newtons. And that is my final answer for the applied force. So hopefully that helps. Remember, all the algebra is the same for all these problems. Your numbers are going to be different than my numbers. So make sure that you are using your numbers when you plug this in to your calculator. Hopefully this helps. Hopefully this makes sense. And this is a better glimpse into how to use these systems to really simplify things. So hopefully that helps. Sweet. I'll see y'all later.